This is the third video in the video series dealing with simple linear regression. I do encourage you to go back and watch the first two videos in the series before watching this video. You might also want to review this video, and I'm speaking here mostly to my students in business statistics. We've covered this already in class, the concept of confidence intervals, but if you need a refresher, go back and take a look at Unit 9, Chapter 9, and also watch this video. There are some other videos also that deal with confidence intervals, but I think if you need a refresher, this one video will be enough of a refresher for you. And because this is a subject that we've already addressed in another unit, I'm going to go pretty fast. I'm going to leave a lot of question marks or a lot of concepts that aren't defined or redefined because they were defined already in a previous unit. If you review Chapter 9, reread Chapter 9, watch the videos and you're still lost, send me a text, give me a call, come by the office, and we'll get you squared away, or we'll try to get you squared away so that you understand what we're doing here. In this series, in this unit, we're dealing with simple linear regression. Simple linear regression can be used to develop a regression equation. The regression equation can then be used to calculate the value of a y variable based upon the value of an x variable. Once we have the regression equation, again, this is covered in video 1 and 2. Once we have the regression equation, all we need to do is plug in the value for x, do the calculation, and that's going to give us a predicted value for y. And it is a prediction. It's not a foolproof, accurate, guaranteed that that's going to be the value. It's an estimate. It's a prediction. There's a chance that it could be off a little bit. There's a chance that it could exist within a range of values. And that's what we have with a confidence interval. A confidence interval is a range of values within which the true value is likely to occur. And when I say likely to occur, it's likely to occur with 95% confidence or 90% confidence or 99% confidence. And when I say 95% confidence, another way of thinking about that, when we calculate a confidence interval, there's a 95% probability, if we're at the 95% confidence level, there's a 95% probability that the true value is going to lie within a particular range. We have the estimate from our regression equation. We use that to calculate a confidence interval. That's going to give us a little bit more understanding of where the real value is likely to occur. I'm going to talk a little bit more about confidence intervals on the next slide. And specifically, I'm going to talk about the difference between confidence intervals and prediction intervals. Prediction interval is a new concept. We covered confidence intervals in Unit 9. Prediction intervals is new, and we'll talk about that more on the next slide. And we're doing this based upon the central limit theorem. The central limit theorem that we've talked about, you're probably sick of the central limit theorem by now, but the central limit theorem allows us to construct these confidence levels and be certain with 95% confidence or 99% confidence that these are good interval estimates for whatever phenomena we're looking at in our analysis. But let's talk about the difference between a confidence interval and a prediction interval. They're closely related. The difference between the two is very subtle, but it is an important difference. And it really goes to how you're using the regression equation and how you're using what you're wanting to predict. With a confidence interval, we're going to have a range of values likely to include the mean for the entire population at a given value of x. Now, in this series, I've been using the analysis of safety training hours and the number of injuries as our example. So let's carry this to the next step, this example to the next step with confidence intervals. The confidence interval is going to be the range for the mean number of injuries likely to occur in a larger population for workers having, let's say, 60 hours of safety training. We could also do it for 61 hours or 69 hours or 150 hours. I'm just using 60 hours here as an example. And when I do the calculations, I'm also going to use 60 hours, but don't get hung up on that 60. It could be, we could plug in any number of training hours into our regression equation to get our estimate. And from that estimate, we could calculate the confidence interval, which is going to be a range within which the true mean for the number of injuries in the larger population is likely to occur, with 95% confidence or 99% confidence or so on. So prediction interval is different. With confidence intervals, we're making an inference about a larger population. With prediction interval, we're focusing on an individual subject. Let's say Jane Doe works for our company and she's had 60 training hours. Based upon her 60 safety training hours, what is the likely number of injuries that she's going to have within, say, a 10-year period? We're focusing on an individual. We're making a prediction about an individual's performance, or the number of injuries likely to be incurred by an individual. Again, the range for the number of injuries likely to be incurred by Jane Doe or John Doe or whoever it may be when she has or he has completed 60 hours of safety training. And it could be 80, it could be 75, it could be 35 hours that we're using. Now the estimate, the regression equation and the estimate's going to be the same for both the prediction interval and the confidence interval, but the calculation is going to be slightly different. The calculation for the prediction interval is going to yield a more conservative range. More conservative range meaning we're going to be more certain that it's within the upper limit and the lower limit of our interval. It's going to be a wider interval. The confidence interval is going to be a narrower interval between the lower limit and the upper limits, and the prediction interval is going to be a wider range between the upper limit and the lower limit. And again, I know I'm throwing a lot of things out here, a lot of concepts out here that you may not know what the heck I'm talking about. You don't know what the heck I'm talking about, you may need to go back and review Unit 9, Chapter 9, and the videos that I mentioned previously. If you're not in business statistics class, in my business statistics class, well, you probably don't have a chance of following this without doing pretty extensive study in advance. What we're dealing with here is Unit 12, the last unit in a 4.5-month semester, and everything we've done in this class up to this point has ended here. This is the culmination of a 4.5-month class. So if you're not in my class, if you're just a casual viewer that stumbled onto this video, you're probably not going to get this without some serious study. So, but having said that, let's move on. Here's another way of thinking about what we're doing with our confidence intervals. At 60 training hours, we use this regression equation. We estimate that there's going to be 5.96 injuries over a 10-year period. Over 10 years of employment, employees that have 60 training hours are going to have 5.96 injuries. This is that point estimate that I mentioned is only an estimate. It's only a prediction. There is a strong probability that that is not the exact number. But we're going to use this value, this point estimate, as the basis for calculating a confidence interval that is very likely to contain the true value. This confidence interval is going to have a lower limit and an upper limit. The upper limit, let's say, for example here, without, just off the top of my head, let's say our point estimate that we have from our regression equation is 5.96 injuries. Our upper limit might be 7.5, and our lower limit might be 4.2. That 4.2 and 7.5, that's the range within which the true population mean is likely to occur or likely to be found. And again, we're doing this based upon a confidence level. Again, 90% confidence level, 95% confidence level, 99% confidence level. If we're at the 95% confidence level, for using that as our confidence level, 95%, there's a 95% chance or 95% probability that the true mean will be between 4.2 and 7.5 injuries, based upon this point estimate. And you can do this for 100 training hours. Our point estimate would be 4.11. 140 training hours, our point estimate would be 2.26. Now we can calculate the confidence interval for each of these levels of safety training. Or you can go, like I alluded to previously, you can go completely away from these nice round numbers that I have here. You could do 81 or 83 or 129. You could plug in 129 hours into this regression equation. That's going to give you the point estimate that you could then use to calculate your confidence interval. This is the formula that we use for calculating confidence intervals from point estimates derived from regression equations. Let's talk about the components of this formula. Y hat, this is our point estimate. This is our predicted value from the regression equation. T, this is a value from a t-table. And if you're in my class, you know all about t-tables and you know how to find t-table values. But we find a value in a t-table based upon our confidence level that we select and the degrees of freedom. Degrees of freedom that we're using when we're calculating these confidence intervals and this particular type of analysis will be n minus 2, where n is our sample size. So if we have 10 subjects, 10 minus 2, we're going to have 8 degrees of freedom. So we'll take that 8 degrees of freedom and the confidence level that we're choosing, whether it's 90, 95, or 99, go to the t-table and find the value that we're going to plug in here. And if none of this is ringing a bell, go back and review previous subjects covered in class and in videos. S sub y x. This is the standard error of the estimate, which we talked about in the second video in the series. So you might, if you haven't watched the second video, go back and watch the second video. It's going to talk about how to calculate the standard error of the estimate and what the standard error of the estimate is. Yeah, it's akin to the standard deviation that we've talked about throughout the semester. But that value, the standard error of the estimate, is going to plug in right there. 1 is a constant. N is our sample size. X sub g, that is the given value of x that we're using, that we use to find our point estimate. The given value of x that we used to calculate our estimate of y using the regression equation. If we want to know how many injuries are likely to occur for a worker who has 60 safety training hours, 60 would be our x sub g value. X bar or bar x, that's the mean from the raw data for the x variable. That's the mean value for safety training hours if we're looking at the relationship between safety training hours and injuries. Once we have these values plugged in, we do the subtraction and we square. We square that result. Now, this term here, this is a summary calculation, the sum of squared deviations, which again, for the business statistics students, we've done this throughout the semester. I'm not going to go into a lot of detail explaining what we mean by this, but the sum of squared deviations, this is a separate calculation that you can do by hand or in a spreadsheet. And I'll mention it a little bit more when we get to the example that we're going to work through. All right, I think that's pretty much covers everything for this formula. Again, we are going to do an example where we're using this formula. Let's go ahead and look at the formula for prediction intervals, which is almost identical. The difference is right here. Underneath the radical, underneath the square root sign, there's a 1 plus that's dropped in there. That 1 plus results in a wider interval, a wider distance between the lower limit of the interval and the upper limit of the interval. It results in a more conservative prediction interval. But that's really it as far as calculating the prediction interval versus the confidence interval. It's pretty much the same. You still use the standard error of the estimate. You still use the predicted value of y based upon the value of x that was plugged into the regression equation. That's all the same. Everything is the same except for this. And the result is a wider interval range, more conservative interval range. And let me reiterate, we use this when we want to create a prediction interval about an individual subject. For example, we want to predict the number of injuries Jane Doe is likely to have in the next 10 years. We're not predicting a mean value for an entire population. We're looking at an individual. All right, well, let's look at a couple of examples. We'll do one example for confidence interval, then one example for prediction intervals. What is the confidence interval for the mean number of injuries likely to be suffered over a 10-year period by workers who have completed 60 hours of safety training? Okay, the first step to solve this problem, if you don't already have your point estimate, you need to take 60 training hours, plug that into your regression equation, which this is our regression equation, and this was developed or calculated in other videos, but we need to plug in 60 in place of x, and that's going to give us our point estimate, which is y hat or y predicted. Okay, let's go ahead and run the numbers and calculate our point estimate using the regression equation and 60 hours of safety training plugged in for x. So we have 8.726 plus negative 0.04617 multiplied by the 60 and enter. 5.9558. Let's round that to 5.96. That's going to be our point estimates. That is going to be plugged into our confidence interval formula for the y hat variable. Let's just go ahead and we got our 5.96 point estimate. We've already talked about the different components in the formula. Our t value based upon 95% confidence level and 8 degrees of freedom. We go to the t table. That t value is 2.306. Plug in for t. We have our standard error of the estimate right here, which we calculated in the previous video, 0.786. 1 is a constant. N, the number of subjects, 10. 10 plugs in for n. X sub G is 60, because we're interested in the Y value, or the number of injuries when there are 60 safety training hours. The mean of X, X bar, bar X, 100.2. We have that here in our summary table. Also, this was used in previous videos. Summary tables are good ideas, or is a good idea when you're doing these kinds of problems, these types of calculations. And the best idea of all is create a summary table in Excel to do a lot of your summary calculations that you're going to use in different formulas. But that's where we're getting the 100.2 right here. The last value in our formula, 20,627.6. That is this term right here, summation of squared deviations, or sum of squared deviations. And let me talk a little bit more about how we get this value. X is the raw score for each subject. Bar X is the mean for the X variable, training hours. So for subject 1, we're going to take 155, the value of X for subject 1, minus the mean of X. And once we have that difference, we're going to square that. We end up with 3003.04. Let me go ahead and do that calculation just to make sure you know what's going on here. We have 155 minus the mean, 100.2. Enter. Now we square this difference, 3003.04, and we do this for each subject in our data set, or each observation in our data set. Once you have this value and all these other values for the other subjects, you sum those, the sum of squared deviations. You have a deviation score squared, then you sum all of those squared deviation scores. In this case, it came out to 20,627.60. Again, that's old hat, I'm sure, for those of you guys. For those of you who are in business statistics, we've talked a lot about the sum of squared deviations throughout the semester. But those are all of our numbers plugged in. Now we need to do some math, and I'm going iteration by iteration. When we perform these mathematical operations underneath the square root sign, we end up with 0.178. And because of time considerations, I'm not going to do each of those, or do all of those calculations for you. You can do those calculations on your own if you don't trust me. But when you do those calculations, you're going to come up with 0.178 underneath the radical. Take the square root of 0.178. It's going to be 0.422. Now we multiply 2.306, 0.786, and 0.422, and that's going to be the product when we multiply those three values. And I'll go ahead and do that one. Let's just let me check my own math, make sure I haven't made a mistake. 2.3. Who knows, maybe I made a mistake when I did this previously. 0.7649, and I rounded that to 0.765. Once you get to this point in the calculation, you're almost there. You have your point estimate plus or minus the margin of error. That's another term for this particular term, margin of error. And 5.96 minus 0.765 is 5.195. 5.96 plus 0.765 is 6.725, and that is our confidence interval. There's a 95% probability that the true mean will be between 5.2 injuries and 6.7 6.73 injuries. That would be for the population of workers with 60 training hours. The true mean for that population of workers with 60 training hours is going to be between 5.2 injuries and 6.73 injuries. Again, this all started with our point estimate, which was 5.96. All right. Well, here's another graphic showing this in more detail with the interpretation. There is a 95% probability that the mean number of injuries over a 10-year period for workers completing 60 hours of safety training will be between 5.2 and 6.73. Let's do a prediction interval. And it's almost identical, so I'm probably going to move a little bit faster here. What is the prediction interval for the number of injuries likely to be incurred by Jane Doe over a 10-year period? Jane has completed 60 hours of safety training. Again, the difference between this and confidence interval. With prediction interval, you're focusing on a specific subject. With confidence interval, you're generalizing to a larger population. Here, individual subject, confidence interval, generalizing to a larger population. The calculations are almost identical. You start with the same regression equation. Plug in 60, the point estimate is going to be 5.96, just like for confidence interval. The only difference is the addition of this term underneath the radical. We plug everything in just like we did before. The t-value is the same from our t-table. We're still at 95% confidence level. We still have 8 degrees of freedom. Our standard error of the estimate is the same, 0.786. Our sum of squared deviations is the same, as is our given value of x and the mean of x. Again, everything's the same except this. And this is going to change the value under the radical. For confidence interval, that value was 0.178. We're adding 1 to it, so we have 1.178. We take the square root of 1.178. We end up with 1.085. Multiply 1.085, 0.786, 0.2306. That gives us our margin of error of 1.967. Subtract that from 5.96 to give us our lower limit of the prediction interval. Add 1.967 to the point estimate to get the upper limit of the prediction interval. And notice it is a wider interval when you're making projections about an individual subject. Adding this 1 in here results in that wider interval. It results in a more conservative estimate. We're 95% confident that the true number of injuries that Jane Doe will incur in a 10-year period is between 3.993 and 7.927. Another way of wording that, there is a 95% probability that Jane Doe, who has completed 60 hours of safety training, will experience between 3.993 and 7.927 injuries over a 10-year period. If you have any questions about prediction intervals, confidence intervals, the difference between the two, send me a text, send me an email, give me a call, come by the office, and we can talk about it in more detail. Also in class, you're always welcome to ask questions in class. All right, that's pretty much it for this video. Just a quick summary here. When we use the regression equation, we're coming up with estimates with some probability of error. Confidence intervals define a range within which the true mean value at a given value of x will be found in a larger population. Prediction intervals are a range of values likely to occur for an individual subject. Again, basically the same procedure for calculating, but the interpretation is different, the application is different, and the prediction interval will be wider than the confidence interval. All right, I'm done with this video. Let me know, as always, let me know if you have any questions.